All right, so yesterday we finished up talking about all of our electrophilic aromatic substitutions. That's all of these guys. I oftentimes abbreviate these as EAS reactions, and I think most textbooks do too, but it's essentially this whole top half portion. These are really versatile, they're very common, and in fact we're going to do a lot of them in lab. However, there's another class of substitution chemistry. If it's not nucleophilic, what do you think it is? Or if it's not electrophilic, what is it? Nucleophilic. There we go. I'm giving it away. So nucleophilic aromatic substitution is another class. Oftentimes people abbreviate this as NAS, right? Not like the server, but the reaction. So let's take a look at an example of nucleophilic aromatic substitution. With nucleophilic aromatic substitution, you can do this reaction with something as simple as hydroxide and then follow it up with an acidic workup. If it's nucleophilic, that means the hydroxide is acting as the nucleophile and not the aromatic ring. In this case, the aromatic ring is acting as the electrophile. So what we're going to do is we're just going to swap off that bromine with an alcohol. There are two key features, though, that you've got to pay attention to when you're doing these sorts of reactions. The first is in order for them to work, you have to have a very strong electron withdrawing group.
Is that step 2 or step 3 for the drawing?
Oh, sorry, that should be step 2. Thank you. The other thing, too, is that you must have a leaving group. Usually this leaving group's in the para position. However, occasionally you might even see it in the ortho position. It works a lot better in the para position. So leaving groups can be bromine, chlorine, iodine. What's another leaving group? Tosylates.
Water.
Yeah, so tosylates. What's the problem of having an alcohol on that side? It's a poor leaving group and you're trying to make an alcohol. So you'd kind of be running around in a circle a little bit. So usually you see halogens in that para position. Let's take a look at the mechanism. All right, so the mechanism is pretty straightforward, but I'm going to try to elaborate on it. What I want you guys to do is to select the carbons on the ring that are electron deficient. Which carbons on the ring are going to be electron deficient relative to the nitro group? Yeah, ortho or para too, right? So if we look at the nitro group, it's electron withdrawing. So each of these carbons is electron deficient. Okay, which means the nucleophile is going to be really attracted to one of these electron deficient carbons. Okay, so this electron deficient carbon is going to be attacked by the nucleophile. Just like we saw before, we're going to break aromaticity. Oh, sorry, I forgot one more arrow. We don't want a Texas carbon, so we have to kick up electrons. So this carbon now has a full negative charge. So basically it's the anionic equivalent to a sigma complex. And I'm just going to draw out the nitro group here. And in this case, we've got a really important resonance contributor, where what you can do is you can kick these electrons down, these electrons over, and then electrons up to the oxygen. So in this case, that negative charge is somewhat stabilized by that electron withdrawing group. Can you guys see that? So each of these oxygens has a negative charge. Again, this has a fancy name. This is referred to as a Meisenheimer complex. Let's see if I can spell this right. It's the anionic equivalent to the sigma complex that we saw in electrophilic aromatic substitution. Okay, so now we're ready to go. In a substitution reaction, we have to kick off our leaving group, though. Yep.
So why wouldn't the hydroxide attack the meta position in respect to the bromine? Because don't halogens kind of activate an ortho pair as well? So wouldn't there be a less deficiency on the meta position?
That's a good question. So if we look at the bromine, it's an ortho para activator relative to itself, right? So in this case, it's going to dump electron density onto this carbon and that carbon and that carbon. This is going to be attracted to an electron deficient carbon, which isn't going to be this position or that position. However, the bromine through induction is pulling a little bit of electron density away from that top carbon, which means it's going to be most susceptible to attack. Okay, so now we've got to figure out how to kick off our leaving group. With this, all we need to do is kick electrons all the way down and kick off that bromine. So it's kind of this domino effect. Okay, so at this point we typically run into a little bit of a problem. This looks like our final product. However, normally we run this reaction in an excess of hydroxide. So this excess of hydroxide will grab this proton and form your phenoxide. Oops, forgot my negative charge. Which is why in step 2 you need to reprotonate this by treating it with a strong acid. Typically, this reaction requires an excess of hydroxide and even a little bit of heat in order for the substitution to occur, which means that your second step always has to be this reacidification step. Does that make sense? So the key things that differentiate this and allow it to occur is you must have a strong deactivator. Ortho or para to a leaving group. If you don't have these two things, this reaction simply won't occur. And like I said, your leaving group is the same sort of leaving group that you guys saw in term 1 with SN2 substitution reactions. So normally it's a halide or a tosylate. All right, there's one last reaction for this chapter that's also similar to aromatic substitution, but slightly different. In fact, you guys saw a little bit of it on last term's final without even knowing it. I wasn't trying to trick you guys, I promise. This is called Elimination Addition. So if we do this reaction, it won't work. Why not?
No electron withdrawing group.
Yeah, no electron withdrawing group. The ring's not deactivated enough. Okay. So what you can do is something else. And let's say I just hit it with a hammer and just really, really crank up the heat. This reaction will work. However, it requires very, very high temperatures and is somewhat impractical. And I'll explain why it works later. There's also another cool reaction that works without a deactivator. And typically we use our old favorite base, sodium amide. And this will also work. And typically, actually, sorry, this is a non-stepwise one. Typically, this is done in a liquid ammonia solvent. When you do this, you can go directly to an aniline, which is kind of handy. So let's take a look at what's going on here. This isn't a simple nucleophilic aromatic substitution. Specifically, it's more of an elimination reaction. So we've got a super strong base and we've got a good leaving group. So let's try to figure out what the elimination reaction would look like. And in fact, I'm going to add on a methyl group here. Where's our beta proton relative to the bromine? Yeah, it's ortho to the bromine position, right? So going back to term 1, we've got a beta proton. So this super strong base can actually reach over, grab this beta proton, clamp down, and kick off our leaving group. Do you guys remember this sort of compound from last term's final? Yeah. Is this aromatic?
Yes.
Yes, right? If we think about the pi system, they have to be aligned. One set of p orbitals is aligned in the triple bond. The other set of p orbitals is actually sticking out and away from the ring. So you can only count one of those p orbitals as a part of the ring system. So this does have 6 pi electrons in the overall ring system. This is still aromatic. And this is a really notorious compound. It's very reactive despite being aromatic, and it's just called benzyne. Okay, now at this step, all you need to do is have your nucleophile add in. So this first step's your elimination step. Next step, we're going to do our addition. And luckily, this addition still works with that sodium amide. However, we run into a problem. The problem is this can attack at that position and kick electrons over, or it could potentially attack, I'll use a green pen, at that carbon and kick electrons over here. They're both somewhat likely, right? Sterically, that methyl group is going to have minimal impact on that side of the ring. It's too far away to really favor attack at the para position or the meta position. So you run into this problem where you create 2 different products. The first one is with that red arrow. Let me scoot this over a little. Oop. And then the second one we'll do with the green arrow. Where the negative charge is right there. And then last but not least, we need to protonate our anion. Come on. There we go. And this is the important reason that we add the ammonia, is the ammonia is really just a weak proton source. Ammonia is a really crummy base, or a really crummy acid, excuse me. But in this case, it's good enough because that aromatic ring is a really, really strong base. This was actually a very famous experiment in order to elucidate the reaction mechanism. They knew that this couldn't be nucleophilic aromatic substitution because they got two different regiochemistries for the product, right? If it were nucleophilic aromatic substitution, you would only get the para-substituted product. The fact that it was also creating this product indicated that it had to go through that benzyne intermediate. The truth is that benzyne isn't a true triple bond. If we look at that benzyne intermediate with the triple bond in the aromatic ring, the carbons on each side are sp hybridized. They do not want to be bent out of linearity, right? So instead, benzyne is kind of a diradical. So it acts more as a radical than as a true alkyne. And it's a very, very unusual molecule that way. So we're not going to get into the weird chemistry behind that, but the key is that it always goes through this benzyne intermediate. The other cool experiment that you can do with benzyne is because it's so reactive, it will actually do Diels-Alder chemistry. And that was another way of showing that these go through benzyne intermediates, is you can throw in a diene and it will react with it super duper quickly. Do you guys want to see that mechanism? Some review?
The benzyne is with the methyl group coming off?
Yeah.
Okay.
So in order to prove that this went through a benzyne intermediate, you can create benzyne, which only exists fleeting, or for a fleeting amount of time, and then you can react it with some sort of dienophile. So we'll react it with furan, which is actually aromatic itself. This can kick over, and kick over. This is our classic Diels-Alder reaction. And we're going to have this bridgehead with oxygen. Whoop. Kind of poking out here, and our double bond over here. So this was another way that they structurally determined that this goes through a benzyne intermediate, was they were able to trap it with something as simple as furan. That wouldn't happen with the intermediate that we saw in the nucleophilic aromatic substitution. Anions don't do Diels-Alder reactions, but this is a really strong dienophile. So very good dienophile. There's a lot of really interesting chemistry going out with strained alkynes because they do a lot of very unique chemistry. So the benefit of using the base as sodium amide is that this requires lower temperature. Or moderate temps. This one requires really high temps. In fact, the one with sodium hydroxide requires such high temperatures it's oftentimes impractical because you'll end up cooking your compound instead of doing the elimination addition reaction that you want. It will just decompose before it even has a chance to occur. So the one with amide is a lot more common. Does that make sense? Okay, so let's take a look at the chapter summary. This was a pretty dense chapter. On the top half, we've got our electrophilic aromatic substitution. That's where we install all of the red functional groups. And then we know we can derivatize those functional groups even further. So in the case of a nitro group, we can reduce it to an aniline. With the methyl group, you can actually over-halogenate it, which we talked about a little bit with our radical chapter, right? So you can add halogens to your benzylic position, which is kind of nice because if we look at toluene, that's an activated aromatic, but when you add on 3 halogens, now it's strongly deactivated. You can change the regiochemistry that way. And then we can oxidize toluene to carboxylic acids, do chemistry with carboxylic acids, or we can reduce a ketone to an alkyl group. So a lot of these are pretty handy. And then the last set that we just covered was nucleophilic aromatic substitution, which we said is different. Instead of the aromatic ring reacting with an electrophile, it's reacting with a nucleophile. And then it only produces one product. The key feature was we had to have a strong deactivator ortho or para to a leaving group. And then with elimination addition, you can see with sodium hydroxide, it requires temperatures of 350 degrees Celsius. Honestly, I've never met a chemist that's actually done that reaction. It's just not very practical. So usually you use sodium amide, but it results in this mixture of stereochemistry on there.
How do we turn the NH2 group into an alcohol?
Not easily. We haven't covered that yet, and I don't think we actually will. If you go on and take advanced organic chemistry, actually, I take that back. We will cover it later this term. I forgot we will. That's later on. So what you have to do to convert an aniline to an alcohol is you actually turn it into a diazonium salt, similar to what you did in lab this week, and then you can substitute it out. So we'll cover that later. So there's kind of this decision making. Most of these reactions are electrophilic aromatic substitution, but some are nucleophilic aromatic substitution, and some are elimination addition. So make sure you're comfortable identifying which mechanism you're going through. And then we covered activators and deactivators and which ones are ortho-para directors versus meta-directors. So this is really the best summary of this chapter that I was able to cobble together. What I've got for you guys is on this last page, I've got a fill-in-the-blank study guide. Oftentimes students will just use this as a study aid, as a way of double-checking themselves. And I would encourage you to actually go out and draw the full reaction mechanism too, including all the intermediates. So what we're going to do with our remaining period is work on some group problems. Yep.
You also said you were going to talk about lab today.
Oh yeah, so lab next week. The updated procedure is now on the class website. Make sure you only plan one reaction at a time. So know what your first reaction is going to be and prep for that entire reaction. After you're done with that reaction, you need to let your product air dry in your drawer. And then you need to get a mass, melting point, and IR of your product. Convince yourself that the reaction worked. If it didn't work, you probably don't want to go on to the next step, or else it's going to cause problems. If it did work, make sure you calculate your percent yield, and then you want to carry a little bit of that product on to the next step. Usually, I recommend that students carry on half of their product to the next step, but leave half behind. Why is that? In case you mess up, you don't have to start all the way over again. That's very, very common. Oftentimes what students will do is, I call it caterpillaring, right? They do one reaction forward, and then the reaction that they left behind, they do that forward the next week, and then they go forward, 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 kind of like a caterpillar inching forward. It's a good strategy. The key is meticulous planning. You need to come in completely ready to go. If you come in and you're rushing, that increases the likelihood of you making a mistake and having to start that reaction over again, especially with the nitration reaction. You need to keep it cold. It says that you need to keep it below 5 degrees Celsius. That means you need to keep it below 5 degrees Celsius. Oftentimes students will squirt in all of their acid, the temperature spikes, and then they form a black goo, and they're not very happy. So make sure that you are very, very careful. Make sure that you're dressed appropriately too. Any other questions about next week? Yep.
Are we going to have pre-lab quiz too?
I think so. I think there's one pre-lab quiz, and that's it.
And there should only be, will it be graded for each week on a notebook entry or just all together?
The notebook entries will be graded all together, but your notebook entry is going to be worth more points than a normal lab. Yeah. All right, so what we'll do with our remaining 20 minutes is work through these problems. So try to get together with a group, and I'll go down the list and ask for volunteers to help explain these.